In this supplement, we'll consider a simple lemma, which is very helpful for computation of asymptotics of loop integrals. Consider the integral, where gamma is a Hankel contour and the real part of z is positive to guarantee the convergence. We'd like to find its asymptotics at large values of z. Function g of t is assumed to have a branch point at t equals 0. Otherwise, the integral vanishes. Hence, the branch cut. See the corresponding figure. Again, we see that the integral is accumulated in a small disk of radius 1 over modulus of z in the vicinity of the origin. In the spirit of the previous asymptotic expansions, we expand the pre-exponential function g of t near the origin. Quite generally, expansion may look as follows, where mu and beta are some arbitrary parameters. The regular branch of g of t is defined as follows. Then the integral can be reduced to the sum of gamma functions. Indeed, let us make a change s equals zt. Each term in the sum is very similar to a Hankel representation for a gamma function. There is one small subtlety though. After the change of variables, the contour, as well as the branch cut, is changed. Namely, they are rotated by angle alpha equals argument of z, counterclockwise. The argument of s variable on the upper and lower branch of the contour is also changed respectively to pi plus alpha and minus pi plus alpha. However, one can still use the same arguments that were employed for the proof of the Hankel representation for the gamma function. To compute the integral representing the term of the sum, first of all, we shrink the contour, as usual, to the combination of two straight lines and infinitesimal circle, and discard the integral around the circle. The last step, namely throwing away the circular integral, is only possible when the real part of mu is greater than -1. But the initial integral is defined for any value of mu, so the answer can be analytically continued on any value of mu. Next, we can actually rotate clockwise the two remaining linear inclined segments so they become horizontal. This way, the linear integrals can be reduced to the combination of gamma functions, quite in the spirit of the derivation of the Hankel formula for the gamma function. The point is, however, as you see from the figure, only the upper part of the contour seems to be able to rotate. The motion of the lower bank is obstructed by the branch cut. This, however, shouldn't cause any trouble. We recall that the multivalued function can actually be spread over several Riemann sheets without the need of the branch cut. Here you see that the branch cut basically serves as a borderline connecting two Riemann sheets of the Riemann surface of the multivalued function of g of t. So the lower segment of the contour can in fact be rotated. It simply slips on the lower Riemann sheet of the Riemann surface of the multivalued function s to mu plus and beta. As a result, the argument of s on the upper and lower branch of the contour becomes again plus minus pi. By the way, I'd like to draw your attention to the fact that the horizontal direction is the direction of the steepest descent for the exponent function as we move from the branch point. Finally, we compute the integral along the upper and lower branches. As usual, introduce a parameterization and perform the integration. As a result, the initial integral is turned into the asymptotic series. And this is basically it. This very formula is called Watson's lemma. Now the question is, how do we apply this simple result?